So today we'll be discussing about the second part of Unit 2. So we'll see what are the components, IIoT components. So today we'll be discussing about ultrasonic sensor, IR sensor, MQ2, that is nothing but we'll be discussing about the sensors like temperature sensor, humidity sensor and so on. So we'll see in detail about all these sensors. So first, we'll see what is meant by ultrasonic sensor. So ultrasonic sensors are nothing but they are electronic devices that calculate the target's distance by emission of ultrasonic sound waves, and it convert those sound waves into electrical signals. So ultrasonic sensors are available for the past many decades, and these devices continue to hold huge space in the sensing market because of its specifications and the affordability and its flexibility. So, as the automation industry has been progressing, the employment of ultrasonic sensors in multiple domains, such as drones, for examples like EV vehicles, is emerging nowadays. When you consider the speed of ultrasonic sensors, uh, the speed of emitted ultrasonic waves, traveling speed is faster than the audible sound. So, uh, in the modern transducer, we can use sonar systems. Along with the solar sensor definition, so we'll see how it works and its specifications. So, how we'll also see how ultrasonic sensors is integrated with the Arduino, and we will see how it is used nowadays. So, once again, I'll tell you. So, ultrasonic sensors are electronic devices that calculate the target distance by emission of ultrasonic sound waves, and these sound waves will be converted into electrical signals. So, next we'll be seeing transmitter and receiver in ultrasonic sensors. So, considering this ultrasonic sensor, so we'll see why we can use ultrasonic sensor. So, for example, like ultrasonic sensors are used for the detection of distance for an extended range of targets. So, irrespective of the surface, we can calculate it. So considering the target surface, color, and shape. So there are two main essential elements in ultrasonic sensors. So we call it as transmitter and receiver. So using the piezoelectric crystals that transmits the transmitter generates the sound, and from there it travels to the target and gets back to the receiver component. So this is all the concept of ultrasonic sensors. So we can say that the ultrasonic sensors are used for the detection of distance extension and for finding out the range. So here ultrasonic sensor working principle, the specification, and how it is integrated with Arduino and its applications we'll see later in this unit. So, to know the distance between the target and the sensor calculates the amount of time required for sound emission to travel from transmitter to receiver. So, this is about the ultrasonic sensors. And here in this slide, we'll be seeing the distance, mainly the distance between the target and the sensor. So the sensor calculates the amount of time required for sound emission to travel from the transmitter to the receiver. So we have a simple calculation. So the calculation is given below. So here the formula is D is equal to 1 by 2 T into C. So here T is represented as time measured in seconds, and C corresponds to sound speed. So it is considered as 343 measured in meters per second. So here we have some ultrasonic specifications. So we have to know what are the specifications of ultrasonic sensor. So For example, the sensing range lies between 40 centimeter to 300 centimeter. So the response time is from 50 milliseconds to 200 milliseconds for ultrasound sensors. So the beam angle is about 50 and it operates within the voltage range of 20 VDC to 30 VDC, and the frequency of the ultrasound wave is 120 kilohertz, and considering the resolution, it is considered to be 1 millimeter. And moving on to the voltage of the sensor output is between 0 VDC to 10 VDC. So, for example, if you consider the weight of ultrasonic sensor, it weighs nearly around 150 grams. So ambient temperature is around minus 250 degrees centigrade to plus 700 degrees centigrade. So the target dimension to measure maximum distance is 5 centimeter cross 5 centimeter. So this is the basic information about the ultrasonic specifications. So knowing all these specification, we'll be able to understand the reliable approximation of distance measurements. So next we'll see what is meant by ultrasonic sensors based on Arduino. So it's nothing but the interfacing of the ultrasonic sensor with the Arduino by considering HCSR04. So where it specifies the ultrasonic sensor pin out and its specification. So we'll see the pin diagram and the other information related to ultrasonic Arduino connection. So this is the diagram which represents ultrasonic uh, sensor pin diagram. So the ultrasonic sensor pin diagram has four pins. Uh, so we have a VCC. So next we have echo, ground and TRIG. So we'll see one by one. So we'll see what is meant by VCC. So VCC is the pin to be connected to a power supply. So that represents 5 plus 5 volt. And TRIG is a pin is used to receive controlling signals from the Arduino board. So this is the triggering input of the sensor. And moving on to the next pin, we call it as echo. So this pin is used for sending signals to the Arduino board. So where the Arduino calculates the pulse duration to know the distance. So this pin is the echo output of the sensor. So next pin we call it as ground. So this pin has to be connected to the ground. So these are the four pins used in ultrasonic sensor. So moving on to ultrasonic sensor block diagram. So we have ultrasonic distance detection sensor. We have servo motor. Signaling conditioning selection is specified, and it is interconnected with ultrasonic distance detection detector. And we have a microcontroller. We call it as Arduino microcontroller. We access with the servo motor. So we have a LCD display. So we'll see how all these things work. Okay. So the target distance is calculated using an ultrasonic distance sensor, and the output from the sensor is provided to the signal conditioning section that is processed during an Arduino microcontroller. So moving on to the result from the microcontroller are fed to the LCD display, and then it is moved to a personal computer. So this is the basic functions, and considering the ultrasonic sensor, it is connected to the servo motor to know the polar distance of the sensor. So considering the rotations of the sensor, it is up to 1800 rotations approximately. And we have so many things related to ultrasonic sensors. So many have doubts whether ultrasonic sensor waves can hurt humans or not. Considering the ultrasonic waves, when there is a long time of exposure to the ultrasound waves, It results in the symptoms such as headaches, dizziness, and some may get a few hearing problems. So people can come across these symptoms when the ultrasound waves frequency crosses 20 kilohertz. So this is about the basic information about the ultrasonic sensors. So initially I told you about the range of the ultrasonic sensor. So here the operating frequency range of ultrasonic sensors is between 300 kilohertz to 500 kilohertz. So this is the basic block diagram. So here in this particular slide, we'll be seeing about the types of sensors related to ultrasonic sensors. So in general, we have ultrasonic sensor which has two sections. Already we have seen that. So it's transmitter and receiver. So these sections are closely placed to the sound travel and it in a straight line from the transmitter to the target, and it travels back to the receiver. So these devices are also termed as ultrasonic transceivers because both the transmitter and the receiver sections are combined in a single unit. So that you have to understand. So it is combined into a single unit, which considerably minimizes the PCB footprint. So here the sensor operates as a burst signal, and the burst signal it is transmitted for some period, and later on the transmission there exists a silent period, and this period is termed as response time. So the response time indicates that it is waiting for the reflected waves, right? So making sure to have a minimal distance between the transmitter and the receiver section, so it delivers minimal errors while calculations. So next we'll move on to timing diagram. So when you learn about ultrasonic sensors, you have to represent the ultrasonic sensor timing diagram. So in detail, we'll see how it can be considered and what should be done to analyze the timing diagram. So consider ultrasonic sensor. So ultrasonic sensor is nothing but we represent that as HCISR04. So where we should provide trigger pulse. So there are so many things where we can specify in a timing diagram. So it produces a sound wave with a frequency of 40 kilohertz. So corresponds to 8 pulses. So this makes the echo pin to the high state. So the echo pin will stay in a high state until and it receives the echo sound. So we have a small procedure to analyze the timing diagram. So already we have seen four pins that is available in the ultrasonic sensor. So considering the TRIG pin, the trigger pulse should be supplied for at least 10 microseconds. So that is what is given in the first trigger signal. So then the device automatically transmit 8 pulses of 40 kilohertz and waits for the rising edge to appear to the output pin. So for example, when the echo pin shows a falling edge, so the timer count is observed. So the count of the timer indicates the time taken by the sensor for object detection and getting back from the object. So therefore, the echo pin width is calculated as the time for the sound to travel from object to from object till it get back. So from the time the distance is measured, and this is termed as sound speed. So as we know, we have seen the formula. So in the previous slide, we have D is equal to S into T. So D is the distance, and we have S is the speed, and T is the time. So distance is equal to speed into time. So the range of HCSR04, that is nothing but ultrasonic sensor, is from 2 centimeter to 400 centimeter. So we have the total distance is measured, and we have seen 343 into time at high echo, the whole divided by 2, right? So this is the calculation of the total distance for ultrasonic sensor. So the total distance is divided by 2 because the sound wave travels from the source to the object and then it returns back to the source. So we specify divided by 2, right? So the echo of the output of echo pin is also shown. So it specifies a propagation delay. So that is also dependent on distance. So it also specifies 40 kilohertz reflected signal along with acoustic burst. So we can see everything in the timing diagram. So next we'll see the factors influencing ultrasonic sensors. So here if you see we have a different target. So the first target is, now we call it as flat shaped target. The second target we call it as round shaped target, and the third type tilted target. So this is the picture which shows the reflection pattern of ultrasonic waves depending on the shape of the target. So there are targets which deflect sound such as human beings, animals, plants, which can result in minimal sensing responses. So in order to generate a high sensing response, a flat target should be towards the sensor at a 90-degree angle. And considering rigid or rough surfaces, so it can show larger angular deviations. So, for example, a radar cross section helps to know how well a target holds the ability to reflect ultrasonic waves. So, for example, if we have a curved or slanting objects, so they scatter most of the ultrasonic signals. So, those are transmitted towards the target and they result in minimal echo response. So, whereas if the surfaces are smooth, flat, and if it is dense, it provides a strong echo responses. So these are the factors influencing ultrasonic sensors. So it's purely based on the target. So these are the advantages of ultrasonic sensors. So it provides consistent outcome and it shows high reliability. So these devices are not impacted by the target's color. So that's the main advantage. So the device shows the flexibility, and in its distance, it a measure the measurement range holds the capacity of measuring the range, and it specifies from few centimeters to 5 meters. So in most of the domains, ultrasonic sensors are widely employed because we have some advantages. So it has a high precision device. So it also provides consistent outcome and it shows a high reliability. So based on the measurements, it can be made every second and it shows a rapid refresh rates. So these are the advantages of ultrasonic sensors. So moving on to the disadvantages of ultrasonic sensors. So even though ultrasonic sensors employ versatile technology, there are also some few limitations. So we'll see some limitations of ultrasonic sensors. So as sound speed is based on humidity and temperature, so the environmental circumstances might show an impact on the accuracy while measuring the distance. For minimal and embedded projects, ultrasonic sensor seems to be not good option. So because these devices are large to integrate with small projects. So if the sensors get dirt, for example, if it is affected by the environmental changes, it results in errors while measuring or the functionality gets impacted. So these sensors will not function in a vacuum. So these are all the limitations of ultrasonic sensors. So considering the application of ultrasonic sensors, so it is used mostly in robotic sensing for positioning of robotic arms. For example, we can say it's used to detect objects, and it is also employed in wash down design for constantly noticing the filling level of objects on a conveyor belts. So The diameter of the coil or the whole roll can be known by ultrasonic sensors. So it is also useful to avoid a collision. So these are all depends on the proximity detection. So next we'll move on to the next type of sensor. We call it as IR sensors. So we call that as infrared sensors. So IR sensors are electronic devices so that detect infrared radiation. So it sends from the surroundings and it is commonly used in applications like remote controls, motion detection and temperature measurement. So if you want to see in detail about the infrared sensor, so it's considered to be an electronic component. So it detects infrared radiation emitted by objects in the environment. Okay. So these sensors can either emit infrared light and it detect its reflection. So we have two types of sensors here. One we call it as active infrared sensors and the second type we call it as passive infrared sensors. So first we'll see what is meant by active infrared sensors. So it simply detect the infrared radiation emitted by objects, right? So that type we call it as active infrared sensors. And moving on to the second passive. So for example, I emit infrared light and it detects its reflection. So there are two types. So already we have seen what is active infrared sensors and passive infrared sensors. So these sensors can either emit infrared light and detects its reflection. So this type we call it as active infrared sensors. And for example, passive infrared sensors is nothing but it simply detect the infrared radiation emitted by objects. So these sensors are widely used in remote controls. It is also used in security systems or we can say obstacle detection in robotics. So this is the main usage of infrared sensors. So basically it's an electronic component so that is used to detect infrared radiation emitted by objects in the environment. So this is the diagram which represents the infrared sensor. Uh, so we'll see what is meant by infrared sensor in detail. So infrared sensor is the one kind of electronic component. This particular infrared technology is used in a wide range of wireless applications, which includes remote controls and sensing. Okay, so these sensors can also be used to detect or measure the heat of a target and its motion. So in many electronic devices, the infrared sensor circuit is a very essential module. So this type of sensor is very similar to humans' visionary sensors to detect obstacles. So so the infrared part in the electromagnetic spectrum of infrared sensor can be separated into three main regions, right? So we can call that three regions as near infrared, mid infrared, and far infrared. So we have three regions. I'll tell you: near infrared, infrared, and far infrared. We'll see about the wavelengths. So the wavelength of these three regions vary based on the applications. For example, for the near infrared region, the wavelength ranges from 700 nanometer to 1400 nanometer, and the wavelength of mid IR region ranges from 1400 to 1400 nanometer to 3000 nanometer, and considering far IR region, the wavelength ranges from 300 nanometer to 1 millimeter. So the near IR region is used on a fiber optic and IR sensors, and the mid IR region is used for heat sensing, and the far IR region is used in thermal imaging. So the range of frequency of IR is maximum as compared to a microwave, and considering it as minimum than the visible light. So this is all about the wavelength, and we have seen the basic ideology of its targets radiation. So the sensor which simply measures the IR radiation instead of emitting passive infrared rays. So generally in the IR spectrum, the radiation of all the target radiation and some kind of thermal radiation are not visible to the eyes, but we can be able to sense through IR sensors. So in this type of sensor, we have IR LED, which is used as an emitter, and whereas the photodiode is used as a detector. Uh, so once an infrared light drops on the photodiode, the output voltage and resistance will be changed in proportion to the received IR light magnitude. Okay, so this is all about the information of infrared sensors. So basically you have to know the three main regions. So the first region we call it as near infrared, the second region we call it as mid infrared, and the third region we call it as far infrared. So we have seen all the three regions about its wavelengths. So in this line we'll be seeing infrared sensor working principle. Okay, so okay, so here we have the arrangement of infrared LED can be done ahead of a photodiode without an obstacle. So as I told you, infrared sensors consist of two main parts. One is the emitter and the receiver. Otherwise, it can be called as transmitter and receiver. So we call this as photocoupler, and here IR LED is used as an emitter, whereas our IR photodiode is used as a receiver. Okay, so IR LED is called as emitter, and IR photodiode is called as receiver. So the photodiode used here, it is very sensitive to the infrared light generated through an infrared LED. So the resistance of photodiode and the output voltage can be changed in proportion to the infrared light which is obtained, and this is the fundamental working of infrared sensors. So considering the infrared sensor module, we'll be seeing about the module which consists of five parts. So the five parts are IRTX, RX, operational amplifier, trimmer port, we call it as variable resistor, and finally we have output LED. So the pin configuration of the IR sensor module is given. So we have three pins. So first we call it as VCC pin is the power supply input, and we have ground pin is power supply ground, and out pin is an active high output. So the main specifications and the features of the IR sensor module is included. So considering infrared sensor, the operating voltage is 5 VDC. Okay, and considering the input output pins, it is 3.3 V and 5 V. So we have a mounting hole, so the range is up to 20 centimeters, and considering the supply current of IR sensor module, it is 20 milliampere, and the range of sensing is adjustable, and we have fixed ambient light sensors. So this is the basic information about the sensor module. And moving on to the types of infrared sensors, already we have seen we have active infrared sensors and passive infrared sensors. So I'll tell you once again about the active and passive infrared sensors. So this type of sensor includes both the emitter and the receiver, which is also known as transmitter and receiver. So in most situations, laser diode or LED is used as a source for Non-imaging infrared sensors, LED is used, whereas the laser diode is used as the imaging infrared sensors. So, we will be seeing about the advantages of infrared sensors. So, it consumes very low power. So, noise immunity is strong, and these sensors are not affected by rust. So, it also detects motion when the light is present or absent. So, they do not need to get in touch with objects for detection. And considering the data leakage, there is no data leakage because of the directionality of infrared radiation of ray. So they are more modest in size, and they are more moderate. So it provides high reliability. So it responds very quickly as compared to other thermocouples. Um, so here we'll be seeing about the disadvantages of IR sensors. So line of sight is necessary, and it can be affected based on the conditions of environment, for example like fog, rain, pollution, dust, etc. So range is also very limited. The data rate transmission is not very fast. So here high force infrared signals can harm human eyes. So these sensors can be blocked with common objects. So these can be the major defect in yeah, infrared sensors. So when you can also consider some applications here. So for example, infrared sensors can be used in applications like rail safety. We can also use it in infrared astronomy, optical power meters, for example like IR imaging devices, uh, for example sorting devices, moisture analysis, night vision services devices, missile guidance. We can also use IR in flame monitors, remote sensing, climatology. We can also use IR sensors in gas monitoring, and we have an application related with photobiomodulation, and we can also it can also be used in exploration of petroleum, flame monitoring, testing of anesthesiology, and even it can be used in gas detectors, moisture analysis, water analysis, and so on. So this is all about the overview of infrared sensors. So this kind of sensor is most frequently used in wireless technology. So where the surrounding objects detection function of remote controlling can be done. So the main feature of this sensor are motion and heat sensing. So considering the infrared rays or the region is not visible to the human eyes. So this is all about the infrared sensors. So here in this slide, we'll be seeing what is MQ2 gas sensor. So we'll see in detail what is meant by MQ2 gas sensor. So sensors are the electronic devices here for the interaction with the outer environment. There are various types of sensors available which can detect light, noise, smoke, proximity, etc. So, these particular sensors are available both in analog and digital forms. So, we have so many types of sensors. So, besides forming a communication with outer environment, sensors are also a crucial part of safety systems. So, for example, we'll be using sensors like fire sensors, which is used to detect the fire, and it take appropriate precautions on time, and for smooth functioning of control system and sensitive electronics. We you can also use humidity sensors, which is used to maintain humidity in the unit. And one of such sensor we are using is MQ2 sensors, which is mainly used for safety systems to detect harmful gases in the environment. So here we'll be seeing about MQ2 gas sensor, the same thing. So MQ2 gas sensor is an electronic sensor which can use to sense the concentration of uh, gases like LPG, propane, methane, hydrogen, alcohol, smoke, carbon dioxide, etc. in the environment. So MQ2 gas sensor is a versatile electronic device, so which is used to identify the presence of gases in the environment, and it can be classified as a chemiresistor. So the sensor operates based on a specialized sensing material. So that material whose electrical resistance varies and when exposed to target gases. So this MQ2 gas sensor is also known as chemiresistor. So it consists of a sensing material, so whose resistance changes when it comes in contact with the gas. So, for example, the sensor operates based on a specialized sensing material whose electrical resistance varies when exposed to target gases. So this resistance change serves as a core mechanism for gas detection, so enabling real-time monitoring and alerting in safety critical applications. And here we will be considering MQ2 sensors. It's a metal oxide semiconductor type gas sensor. So concentrations of gas in the gas is measured using a voltage divider network which is present in the sensor. So this sensor works on 5V DC voltage, and it can detect gases in the concentration of range ranging from 200 to 10,000 ppm. Uh, and here we'll be seeing about the working principle of MQ2 sensors. So when reducing gases are present, these oxygen atoms react with the reducing gases, thereby decreasing the surface density and the oxygen. So this sensor contains a sensing element, mainly aluminum oxide based ceramic, so which is also coated with tin dioxide, and it is enclosed in a stainless steel mesh. So we have seen the diagram initially. So sensing element has six connecting legs attached to it. So two legs are responsible for heating the sensing element. The other four are used for output signals. Now current can flow through the sensor, which generates analog voltage values. So these voltage values are measured. So after measuring, we can know the concentration of gases. So voltage values are higher when the concentration of gas is also high. So then the donor electron present in tin oxide are attracted towards this oxygen, thus preventing the current flow. So this is the basic working of MQ2 sensor. So these sensors are used to detect the presence of gases in the air. For example, I told you before, such gases like methane, butane, LPG, and smoke. But they are unable to distinguish between gases. So, mm so this sensor can be used without interfacing any microcontroller, and it is useful when detecting only one particular gas. So this can also detect the gas, but if ppm has to be calculated, then the sensor should be used without a module. So this sensor is also used for air quality monitoring. So it can also produce gas leak alarm, and for maintaining environmental standards in hospitals, in industries, etc. So these are used to detect the leakage of harmful gases. So, so some of the alternative of MQ2 gas sensors are also there. So, for example, MQ6 is also a type of gas sensor. M306A is also a gas sensor, and replacing MQ2 gas sensor, we can have a sensor called as AQ3 sensors. So these are the types of sensors used instead of MQ2 sensors. So next, moving on to the next part, we will have temperature and humidity sensors. So humidity is defined as the amount of water present in the surrounding air. So sensing, measuring, monitoring and controlling humidity is a very important task nowadays. So some of the important areas of application for sensing, measuring and controlling humidity are mentioned. For example, like domestic sensing, controlling humidity in our homes and offices or in industry is very important, and gives higher humidity conditions will affect the blood flow. So there are also two types of humidity we can consider here. So absolute humidity and relative humidity. So first we'll see absolute humidity, sorry. So it doesn't take temperature into the account, but it changes with the temperature and pressure. So generally we have to consider the moisture. So the term moisture means water content of any material or substance. But practically we can say the term moisture refers to the water content in solids and liquids. um, so first we'll be seeing what is meant by relative humidity and absolute humidity. So relative humidity, whenever we talk about measuring humidity, it is usually relative humidity that we are talking about. We have RH, which is the ratio of the actual water vapor pressure present in the air. So at a temperature to the maximum water vapor pressure present in the air at the same temperature. So moving on to the absolute humidity, it is the ratio of mass of water vapor to the volume of the air. So if m is considered as the mass of the water vapor and v is the total volume, so the volume of air and water vapor mixture, then absolute humidity Ah is given by m divided by v. So m is the mass and v is the total volume. So this is how we will be denoting it. So in some weather reports and forecasts, the probability of precipitation or dew or fog is indicated using relative humidity, and hence it is considered as an important metric in the environment. So moving on to the relative humidity, it takes both temperature and pressure into the consideration. So here we'll be dealing with the measure of relative humidity. So measuring both the moisture content as well as the air temperature. So for temperature above 1000 degrees centigrade, measuring relative humidity RH is no use, as it would deliver misleading values. So this is the basic ideology of absolute humidity. And here already I have told you about humidity, and here we'll be seeing about specific humidity. So a specific humidity is considered as SH. So it is a ratio of mass of the water vapor to the total mass of the air, so that we call it as specific humidity. So mixing ratio or the humidity ratio is the ratio of mass of the water vapor to mass of the dry air. So there are so many things we can consider here. We have dew point temperature. So dew point temperature is the temperature at which the water vapor content is saturated in the air. So you have to know what is meant by dew point temperature. For example, at dew point temperature, the relative humidity RH is 100 percentage, and we can say in other words, for example, for the air to hold maximum amount of water vapor or moisture, it has to reach dew point temperature. So basically dew point temperature is nothing but the temperature at which the water vapor content is saturated in the air. So we have so many types of humidity sensors. So when, for example, when you're purchasing a humidity sensor, you can choose from one of these three varieties. So we have capacitive humidity sensor. So this is a linear sensor measure which measures the relative humidity from 0 percentage to 100 percentage humidity. So it features a metal strip where it is placed between two electrodes, and we have the next type that we call it as resistive humidity sensor. which has ionized salts between two electrodes. So the resistance of the electrode changes when the humidity level goes up or down. So the next type we call it as thermal humidity sensors. So here we use two separate sensors, one in a layer of dry nitrogen and other measuring the ambient air. So the difference between the two measurements in the humidity level should we have to keep that in mind, that capacitive and resistive sensors measure relative humidity, while thermal sensors detect AH values. So next we'll move on to working principles of capacitive RH sensors. So here we'll be considering humidity sensors, where we have very important devices that help in measuring the environmental humidity. So a simple capacitive RH sensor can be made from an air-filled capacitor. As the moisture in the atmosphere changes its permittivity, and for some practical application, air as a dielectric is not feasible. So technically we can say the device used to measure the humidity of the atmosphere is called as hygrometer. Okay, so the device which is used to measure the humidity of the atmosphere is called hygrometer. And the humidity sensor or hygrometers can be classified based on the type of humidity it is used for measuring. Okay, so here hence the space between the capacitor plates is usually filled with an appropriate dielectric material. So we call it as isolator, whose dielectric constant varies when it is subjected to change in humidity. So the most common method of constructing a capacitive RH sensor is to use a hygroscopic polymer film as dielectric and depositing two layers of electrodes on the other sides. So absolute humidity, that is AH, or relative humidity RH sensors can be used here, and humidity sensors can also be classified based on the parameter used for measuring humidity. That is, for example, capacitive humidity sensors, electrical conductivity or resistive sensors, humidity sensors, and thermal conductivity humidity sensors can be used. So there are also other types of humidity sensors or hygrometers, like optical hygrometer, oscillating hygrometer, uh, gravimetric hygrometer. So we will be having so many types here. So we can see all these working principles. So which has the basic working principle of a normal sensor. So another way is to use the capacitive RH sensors, which is used to observe the changes in the frequency of the oscillator. So the oscillator constructed using a capacitor, and we have RH sensitive test subjects as dielectric poles. So this setup is often employed in pharmaceutical products. So it also consists of protective polymer layer. So when you consider this type of sensor, it has varying layers. So it consists of a protective polymer layer, and after protective polymer layer we have porous platinum layer. So that particular layer we call it as an electrode, and next to the electrode we have polymer layer dielectric, and finally we have platinum layer, that is also an electrode, and finally we have a substrate silicon layer. So this is all about the working of capacitive RH sensors. The test samples like medical tablets are placed between two plates, which form the capacitor electrodes to form a capacitor in the LC oscillator circuit. The frequency of the oscillator changes with the humidity surrounding the test sample. So here let us see the construction of a thin thermostat polymer film. based on capacitive RH sensor. So it is nothing but it is fabricated on a silicon substrate. So on this substrate, there are two metal electrodes. So the metal electrodes are made of either aluminium, platinum, or chromium. So these are all not deposited. Okay, so the shape of these electrodes is carved out such that the electrodes form an interdigitized pattern. So on the top of this layer, and dielectric layer is deposited. So for example, we have varying representation of the capacitive humidity sensor. So here two temperature sensitive resistors are deposited on the same substrate to provide temperature compensation. So we have a diagram representing capacitive RH sensor where we have the test samples in between the capacitor plates, and we have an oscillator, and finally we have a counter. So we will see about the advantages of capacitive humidity sensors. So the output voltage is very linear. So they provide stable results over long usage. So capacitive humidity sensor can also detect wide range of RH. So moving on to the disadvantages of uh, capacitive humidity sensors. The distance from the sensor and signaling circuit is very limited. So we can consider that as a disadvantage. So moving on to the next part, we have resistive humidity sensors. We can also call that as electrical conductivity sensors. So resistive humidity sensor is nothing but that measure the resistance. For example, impedance we can say, or we can call it as electrical conductivity. So the principle behind resistive humidity sensor is the fact that the conductivity is non-metallic conductors and it is dependent on their water content. Okay. So we can see the working principle of resistive humidity sensors. So here we have um, uh, an electrode, so that is placed in interdigitized pattern to increase the contact area. So the resistivity between the electrodes changes when the top layer absorbs water, and this change can be measured with the help of a simple electric circuit. So this resistive humidity sensor is usually made of materials with a relatively low resistivity, and this resistivity changes significantly with changes in humidity. So the relationship between this resistance and humidity is inverse exponential. So the low resistivity material is deposited on the top of two electrodes. So already I told you the electrodes are placed in the interdigitized pattern to increase the contact area. So the electrodes changes when the top layer absorbs water, and this change is measured with the help of a electric circuit. So here we'll see the working of resistive humidity sensors. So we have a conductive layer on the top, and we have electrode in between, and we have two terminals. Okay, so some of the commonly used materials are salt, and here we'll be using some substrates, for example like solid electrolytes and conductive polymers. So there are also some modern resistive humidity sensors which are coated with ceramic substance, so which also provide an extra protection. So we mainly use modern resistive humidity sensors with an ceramic substance to provide extra protection. So these electrodes in the sensor are usually made of noble metals like gold, silver, or platinum. So considering the benefits of humidity sensors, so there are so many advantages. So it includes increasing energy efficiency. So humidity sensor provides real-time information about the level of moisture in the air. So it is very easy to optimize the temperature airflow and the ventilation and reduce energy consumption. Moving on to some other advantages, we can have achieving precise climate control. For example, when you know some current moisture levels, you can make adjustments to environmental conditions, and it can improve occupant satisfaction. So it can also prevent mold and mild dew. A humidity sensor detects excess moisture, which promotes potentially harmful mold and mild dew growth. So maintaining industrial environments is easy. Because humidity levels can affect machinery performance and product quality, and industries like pharmaceuticals use sensors to ensure it stays within an acceptable range. So it has a wide application in the pharmaceutical companies. So these benefits of humidity sensors ultimately help you cut cost, it can streamline the operations, and it can establish a comfortable work or living environment. Uh, So moving on to the advantages of resistive humidity sensors, we have it's very low cost, it's very small in size. So the distance between the sensor and signal circuit can be large, and it is suitable for remote operations. So it is highly interchangeable, and there are no calibration standards here. So these are the main advantages of resistive humidity sensors. And moving on to the disadvantages, we have uh, 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 these sensors are really very sensitive to chemical vapors and other contaminants. So the output readings may shift if used with water soluble products. So there are also numerous applications of resistive humidity sensors. Um, these resistive or electrical conductive humidity sensors are low cost sensors with the size is really very small. So they are often used in several industries, domestic or residential or commercial purposes. And considering the thermal conductivity humidity sensors, they are also known as absolute humidity, where AH sensors they can measure the absolute humidity value, and the thermal conductivity humidity sensor measure the thermal conductivity of both dry air as well as air with water vapor. So the difference between the individual thermal conductivities uh, can also be related to absolute humidity. Uh, so, when we consider the working of thermal conductivity humidity sensors, we have a thermal conductivity based humidity sensor. So, we call that as thermistor. So here we have two tiny thermistors with the negative temperature coefficient. Which is used to for bridge circuit. So I told you we have two tiny thermistors with negative temperature coefficient, which is used for bridge circuit. So in that, one thermistor is used or sealed in a chamber filled with dry nitrogen, uh, while on the other hand it is exposed to open environment through small venting holes. When the circuit is powered on, the resistance of the two thermosists are calculated, and the difference between those two values is directly proportional to absolute humidity. So these are the basic working principle, and we can consider some important considerations when selecting a humidity sensor. So we can consider a humidity sensor based on the accuracy of the sensor, calibration based on the requirements and the methods used, size of the sensor, cost of the sensor, and the cost of replacement can also be considered. Output repeatability, circuit complexity. We can also consider based on resistance to contamination, reliability of the sensor, and so on. So these considerations can be included in a humidity sensor. So we have numerous things to consider in a resistive humidity sensor. So the thing is, we have temperature coefficient, so that is used to build or bridge circuit, is used for a bridge circuit. So that is the concept you have to understand here in resistive humidity sensor. And now I will be completing this portion, and the next video will be learning about the switches and the types. Thank you all. Uh, Thank you once again.